Hello, good evening dear friends. This is the simplest and easiest way of teaching learning process in our most popular YouTube channel Physics Make It Simple by Dr.Rajendra Kobarne, now working as a principal in Loknete Dr. Balasaheb Vikhe Patil, Padma Bhushan Awardee, Pravara Rural Education Societies, Mahatma Phule Vidyalaya and Junior College, Dad Budruk Taluka, Rahata. As long as 12 science oscillation is concerned, this is the lecture number 13, and in this lecture we want to discuss about magnet vibrating in uniform magnetic field of induction B or magnet oscillating in uniform magnetic field of induction B. Let us see the diagram. The diagram is like this. These black arrows suggest uniform magnetic field B, and initially the magnet is placed along the direction of the uniform magnetic field of induction B. If this magnet is displaced by an angle theta, suppose like this, the magnet is displaced by an angle theta and left itself to oscillate, then magnet starts oscillating like this. As soon as the magnet starts oscillating like this, two forces are acting on north pole and S pole. Force acting on north pole is Qm into B vector, which is in upward direction. Force acting on S pole is in downward direction, which is equal to minus Qm into B. These two forces are having equal in magnitude but opposite in direction. Try to restore the magnet to its original condition. These two forces forms a couple, and forming a couple, that couple acts as a restoring torque. Try to restore the magnet to its original condition. Okay, so what is Qm? Qm is pole strength of the magnet plus Qm is pole strength of N pole and minus Qm is pole strength of S pole. Qm into B is upward force and minus Qm into B is downward force. These two forces are having equal in magnitude but opposite in direction. Combination of these two forces that I have already told form a couple, and because of having this couple, these couple try to restore the magnet to its original condition like this, forming a restoring torque. And so that formula of restoring torque tau is equal to one force into perpendicular distance between two forces. So this is one force, this is another force. Extend this line below, extend this line horizontal. So this SP is a perpendicular distance between minus QMB and plus QMB. This SP is a perpendicular distance between two forces. So restoring torque tau, remember well dear students, the formula of restoring torque tau is given by the relation tau is equal to magnitude of one force into perpendicular distance between two forces. So magnitude of any one force is Qm into B, that I have written here, Qm into B, and perpendicular distance between two forces is length of SP, length of SP. So what is the formula of length of SP? Consider the triangle SPN. This triangle we have considered. From triangle SPN, I have shown sin theta. What we get sin theta? Sin theta is equal to SP upon Sn. So length of Sn is equal to 2L, that is magnetic length of the magnet. So SP, length of Sn is equal to 2L. So length of SP we got is 2L sin theta. This is equation 1. So in this way, length of SP we got is 2L sin theta. Put this value of length of SP here. We get what here? See here. Length of SP is equal to 2L sin theta. So here Qm, I have reshuffled the equation. This 2L I have taken here. This B is here, sin theta. This is equation 2. Then let us think about the product of Qm into 2L. This Qm into 2L is nothing but, dear students, magnetic dipole moment. Remember well, magnetic dipole moment is a vector quantity directed from south pole to north pole, and this magnetic dipole moment is denoted by mu. By putting Qm into 2L is equal to mu, which is equal to magnetic dipole moment, in equation 2 we get equation 2, tau is equal to mu b sin theta. Remember well, we displace the magnet making use of very small angle. If theta is very small, then we always know, many times we use this. If theta is very small, sin theta is approximately equal to theta. That I have put here. And by putting sin theta is approximately equal to theta, we get tau is equal to mu b theta. Then observe the diagram. Deflecting torque is acting along this direction, in anti-clockwise direction, while angular displacement is directing along clockwise direction. So deflecting torque and angular displacement theta both are opposite direction. I will repeat again. Restoring torque, deflecting torque acts as a restoring torque. This restoring torque is along anti-clockwise direction, while angular displacement is along clockwise direction. So restoring torque tau and angular displacement theta both are acting in opposite direction, and so the negative sign is given here. Tau is equal to minus mu b theta. I have taken minus sign here because tau and theta are oppositely directed. That I have written here. If tau and theta are oppositely directed. But here remember well, dear students, this mu and b are constant. If this mu and b are constant, we can easily write tau is directly proportional to minus theta. And this is a definition of angular SHM that we have already known, we have already learned in lecture number 12. Please listen lecture number 12. In that lecture number 12, we have discussed about definition of angular SHM, and definition of angular SHM is formed by making use of equation tau is directly proportional to minus theta. So this equation we get here, tau is directly proportional to minus theta. It clearly indicates that restoring torque tau, the magnitude of restoring torque tau is directly proportional to angular displacement theta, and both restoring torque tau and angular displacement theta are oppositely directed, and this is the definition of angular SHM, and so that we can write vibration of the magnet in uniform magnetic field performs angular SHM. So there may be a possibility of asking the question like this: show that magnet vibrating in magnetic field B performs angular SHM. So we should come up to this: tau is directly proportional to minus theta, and if this equation we get, it clearly indicates that motion of the magnet when placed in uniform magnetic field performs angular SHM. So this is the part 1, and then now we'll have to discuss part 2, and in part 2, dear students, we have to derive the formula of period of a magnet when placed in uniform magnetic field. Okay, we will clean the board at first, and then we will discuss about period of a magnet. Okay, I will clean the board at first. Period of a magnet. Period of a magnet. Okay. We have seen magnet vibrating in uniform magnetic field performs angular SHM. Then we have to discuss about period of a magnet. Okay. We will see period of a magnet, part 2. Part 2, period capital T of a magnet. Okay, we know what we know. We know what? Tau is equal to minus mu b theta. Take magnitude only. Take magnitude only. Take magnitude only. After taking magnitude only, we get tau is equal to mu b into theta. This is equation number what? This is equation number suppose 4. We also learned in rotational dynamics that is tau is equal to I alpha. So we can write, I will change the pen, tau is equal to I alpha, where I is a mi of a magnet about particular axis and this alpha is angular acceleration. This is equation 5. Comparing 4 and 5, comparing equation 4 and equation 5, we get what? We get like this. I alpha is equal to mu b into theta. Okay. Then I will reshuffle this equation like this. Alpha upon theta is equal to mu b upon I. What is alpha upon theta? Alpha is angular acceleration and theta is angular displacement. So this is what? Angular acceleration per unit angular displacement. So we will write here angular acceleration, alpha per unit angular displacement theta is equal to mu b upon capital I. This is equation 6. So we know period of angular SHM, that general formula we write. Period of angular SHM is equal to 2 pi upon square root of angular acceleration per unit angular displacement square root. So square root of angular acceleration per unit angular displacement, that we know, which is equal to mu b upon I. So period of angular SHM is denoted by capital T. So capital T is equal to 2 pi upon square root of mu b upon I, like this. And by reshuffling this equation, we get what? Capital T is equal to 2 pi square root of I upon mu into b. By making use of this formula, we can derive the period of a vibrating magnet. Capital T is equal to 2 pi square root of capital I upon mu b, where capital I is mi of a magnet about a particular axis and mu is magnetic dipole moment and capital B is magnetic field. Okay. By making use of this formula, we can derive period of a oscillating magnet, vibrating magnet in uniform magnetic field. So another question is asked like this: derive the formula of a period of vibrating magnet when placed in uniform magnetic field. And the first question that I have already discussed, show that motion of the magnet in uniform magnetic field performs angular SHM. These are the two questions. When the motion of the magnet performs angular SHM, we come up to this. Not necessary to derive period. But if we obtain the formula of period, then we should come up to this. Capital T is equal to 2 pi square root of capital I upon mu b. This is all about period of a magnet vibrating in uniform magnetic field. We will stop here. Let us listen this article again and again. Take a screenshot to write a simple note that I have written on the board in your notebook. Subscribe my channel and let us be alert. Let us remain attached to my channel, and we will meet again for the next lecture by taking next article. Goodbye.